Welcome to AI Cooper Podcasts. Today we are tackling one of the absolute biggest bottlenecks in training large language models.
Yeah, that classic trade-off between stability and efficiency.
Exactly. And the paper we're looking at is titled Adam Improves Muon, Adaptive Moment Estimation with Orthogonalized Momentum. It's coming out of UCLA from researchers Mingxin Zhang, Yuxuan Liu, and Hayden Schaefer.
And if you've been tracking the optimizer wars lately, you know this is a massively significant one.
Oh, absolutely.
We already know Muon is incredible at exploiting the matrix structure of neural networks using orthogonal updates, but it really suffers from instability in stochastic settings.
Right, because it just lacks a mechanism to handle noise,
Yeah.
which is what this paper solves. They propose two new optimizers, NAMO and NAMO-D. NAMO basically applies a global scalar to the orthogonal update based on the signal-to-noise ratio.
Preserving strict orthogonality, yeah.
Exactly. And then NEMOD takes it a step further with a diagonal matrix update, adapting step sizes neuron by neuron.
And the results are just stellar. On GPT-2 pre-training tasks, both the 124 million and 355 million parameter models, both NAMO and NAMO-D, outperform AdamW and standard Muon baselines.
NEMOD specifically achieves the lowest validation loss overall. It effectively stabilizes the geometry-aware updates of Muon with the variance reduction techniques of Adam.
Best of both worlds, really.
Yeah. So that's the high-level summary, but let's actually get into the weeds here. I think most of you listening are probably familiar with AdamW.
It's the bread and butter of the industry.
Right. And recently, Muon has been making waves. But why did we need to merge them in the first place? Like, what is the fundamental friction here?
Well, it really comes down to how these optimizers view the parameter space. Adam, and AdamW by extension, views parameters as a flattened vector.
Just a long list of numbers.
Exactly. It doesn't care if those parameters are part of an attention head, a perceptron, a convolution, whatever. It just treats them as a coordinate list. And its strength is coordinate-wise adaptive step sizes.
So it looks at the variance. Like, if a specific parameter has a noisy gradient, Adam scales down the step size.
Right. It's a built-in safety mechanism.
It's checking that signal-to-noise ratio constantly.
Precisely. And that is why Adam is just so robust. I mean, you can throw it at almost anything and it will converge. Muon, on the other hand, comes from a totally different philosophy.
It actually treats the layers as matrices.
Which they are. It uses singular value decomposition, or SVB, to orthogonalize the momentum update.
Which effectively acts as steepest descent under the spectral norm, rather than just the Euclidean norm.
Yes, exactly. And in the context of deep learning, especially with transformers, maintaining that spectral structure is huge for efficiency. It keeps the layers really well conditioned.
But here Muon has a fatal flaw in stochastic settings.
Yeah. Its orthogonalization operation is completely unbounded.
Unbounded meaning it doesn't know when to pump the brakes.
It doesn't know how to pump the brakes based on noise. Think about it. If your mini batch has high variance,
which is pretty much always true in LM training.
Right. Muon takes that noisy gradient, forces it to be orthogonal, and potentially takes a massive step in a terrible direction.
Oh, wow. So it actually amplifies the noise.
Exactly. It amplifies it because it lacks that variance-based adaptation that Adam has built in.
Okay, so the core mission of this paper is to keep the matrix smarts of Muon, but add the noise filters of Adam.
That's a great way to put it.
So let's talk about their first implementation, NAMO. Algorithm 1 in the paper.
Yeah, so NAMO stands for Norm-Based Adaptive Moment Estimation with Orthogonalized Momentum. The mechanism is surprisingly clean. You calculate your momentum and you orthogonalize it, just like standard Muon.
So that gives you your update direction.
Right. But instead of applying it directly to the weights, you scale it.
You calculate a global adaptive scalar. I think they call it alpha sub t.
Yep, alpha sub t. To get this scalar, NAMO calculates a biased first moment and a biased second raw moment. But here is the critical difference from Adam. Instead of doing this element-wise, it uses the squared Frobenius norm of the gradient matrix.
The Frobenius norm. So that's essentially looking at the aggregate energy of the matrix, right? It's measuring the total noise level of the entire layer.
Correct. It computes the ratio of the global signal to the global noise. If the layer as a whole is noisy, alpha subkey drops below 1. It scales down.
And if the signal is strong,
it stays high. And then it multiplies the entire orthogonal update matrix by this single scalar.
And because it's a scalar multiplication, strictly speaking, this preserves the orthogonality of the update perfectly.
Exactly. The geometry of the matrix doesn't change, only the magnitude.
That's the main selling point of NAMO, then. It creates a safe, bounded version of Muon without breaking those spectral properties that make Muon so fast to begin with.
Yep.
What about the computational cost, though? calculating all these norms?
It's O of MM. In the world of large-scale training, that's completely negligible. It adds virtually no memory overhead compared to standard muon.
Okay, so NEMO is the safe global fix. But then the authors argue that a global scalar might be too coarse.
Yeah, because think about a standard weight matrix. If I have a matrix with 4096 columns representing 4096 neurons, surely they aren't all experiencing the exact same noise level at the exact same time.
Right. Applying one single learning rate scalar to that whole matrix is probably suboptimal.
Exactly. You might be underdamping a really noisy neuron and overdamping a clean one. And that's the motivation for NEMO-D. The D stands for diagonal.
Right.
The authors point out that neural network Hessians, the curvature of the loss landscape, they often exhibit a near block diagonal structure.
Meaning that different columns or neurons act fairly independently of each other.
Right. So NAMO-D solves the coarse scaling issue by replacing that global scalar alpha sub t with a diagonal matrix, D sub t.
Okay.
It tracks the norm of the jth column of the stochastic gradient to create a neuron-wise adaptive step size.
Now that sounds a lot more like Adam, which is element-wise. Here, we're column-wise. But wait, there's a catch here.
There is.
If I take an orthogonal matrix and I multiply it by a diagonal matrix.
You break the orthogonality.
Right. An orthogonal matrix scaled by non-uniform values isn't orthogonal anymore. So aren't we just destroying the very thing that makes muon special in the first place?
And that is the central tension of NAMO-D. You are actively trading strict orthogonality for fine-grained noise adaptation.
Seems risky.
It is, which is why the authors introduce a safeguard to prevent the geometry from being completely wrecked. They call it clamping.
This is the hyperparameter C, right?
Yes, the clamping parameter C. It sits between 0 and 1. Basically, the algorithm calculates the average step size across the diagonal. Then it enforces a hard rule.
Which is?
No individual neuron step size can deviate too far from that average. The parameter C defines the maximum allowable ratio between the max and min elements of that diagonal matrix.
Okay, let's run the edge cases so people can visualize this. If C equals 1.
If C equals 1, the ratio is locked tight. Every element on the diagonal must be exactly equal to the average.
So you effectively revert back to standard NAMO. You just have a global scalar, and strict orthogonality is preserved.
Exactly.
And what if C is close to 0?
Then you allow very aggressive adaptation. One neuron could have a step size 10 times larger than its neighbor. You are heavily prioritizing the signal-to-noise ratio over the matrix geometry.
So it's basically a sliding scale between pure geometry on one end and pure adaptivity on the other.
Yeah. And tuning this parameter turns out to be incredibly revealing about how different models behave, which we'll see when we get to the experiments.
Yeah, I definitely want to talk about those GPT-2 results. But before we do, I want to touch on the theoretical guarantees.
Oh, the math.
Right, because usually when we start hacking optimizers together, like, oh, let's just multiply a diagonal matrix here and let's clamp it over there.
You lose the ability to actually prove convergence.
Exactly. It just becomes a heuristic mess. But this paper is really rigorous.
It is. They provide comprehensive convergence analysis for both deterministic and stochastic settings. In the deterministic setting, both NAMO and NEMO-D achieve an optimal convergence rate of O of t to the -1/2.
Which matches the lower complexity bound for smooth, non-convex optimization.
Right.
So theoretically, it's literally as fast as you can mathematically get.
In a worst-case scenario, yes, but the stochastic setting is what actually matters for us training LLMs.
Right, because of the noise.
Exactly. They show that the convergence rate adapts to the noise level, sigma. It achieves O of t to the -1/4 when the batch size is sufficiently large.
I think they specified when the batch size scales with the square root of t.
Yes.
So the big takeaway for listeners here is that adding this Adam-style variance adaptation doesn't break the math.
Not at all.
It mathematically stabilizes the orthogonal descent against noise without ruining the convergence properties.
Correct. It puts the whole method on really solid theoretical ground rather than just being a neat trick.
Okay, let's talk about the experiments, because this is where the rubber meets the road. They tested this on a GPT-2 pre-training using the Open Web Text dataset.
Yeah.
And they trained two different sizes, right? A 124 million parameter model, which is GPT-2 small, and a 355 million parameter model, GPT-2 medium.
Right. And the baselines they tested against were AdamW and Muon. And it's worth noting here that for the muon baseline, they used muon for the 2D matrices and AdamW for the 1D vectors and scalars.
Which is the standard way you implement muon anyway.
Exactly.
So who won?
Well, both NAMO and NAMO-D achieved lower training and validation loss than both AdamW and standard muon. It was a very consistent improvement across the board.
Awesome. But the really interesting nuance is the comparison between NAMO and NAMO-D, right? Because NAMO-D allows for that column-wise adaptation.
Yes. For the 124 million parameter model, NAMO-D achieved the lowest validation loss after 50,000 steps. And the optimal clamping parameter, C, for that model was 0.1.
Wow. 0.1 is a very loose clamp.
Extremely loose.
That implies that for the smaller model, letting individual neurons adapt aggressively was actually more beneficial than preserving the strict matrix structure.
Exactly. The Adam part of the hybrid was doing the heavy lifting there, but then look at what happens with the 355 million parameter model.
Right. NAMO-D still won, but the optimal clamping parameter shifted all the way to 0.9.
Yeah.
0.9 is extremely tight. That's almost reverting to NAMO.
It really is. It strongly suggests that as the model scaled up, preserving the condition number of the update, keeping that geometry intact, became much more critical.
So the larger the matrix, the more dangerous it is to let columns diverge in step size.
Precisely.
That feels like a massive scaling law observation. Like if you're training a 70 billion parameter model, you might need C2 be 0.99, or maybe you just stick to standard NAMO.
It's certainly a hypothesis worth testing. It really hints that structure awareness becomes the dominant requirement at scale, while noise management needs to be more global rather than local.
Fascinating. Now, the other set of graphs in the paper that really jumped out at me were the robustness plots. They plotted the final loss against the learning rate.
Oh, the U-shaped graphs.
Yeah. And for engineers deploying these models in the real world, this is arguably more important than the final loss number itself.
Absolutely, because hyperparameter tuning is so expensive.
Right. If you look at the curve for standard muon, it is a really deep, narrow V-shape.
Very brittle. If you hit the optimal learning rate perfectly, great. But if you miss it even slightly, performance just degrades incredibly fast.
And then look at NAMO.
It's a wide, flat basin. I mean, you could vary the learning rate by nearly an order of magnitude and still get near optimal performance.
That is just the atom stability shining right through.
It really is. The variance adaptation absorbs the shock of a suboptimal learning rate. It means you spend significantly less compute on hyperparameter sweeps.
Now, for NEMO-D, you do have to tune that sig parameter.
True, but the learning rate sensitivity itself is drastically reduced, which is the really expensive part to tune.
Makes sense.
Yeah.
Now, I want to dig into the implementation details a bit because there's some clever stuff here. We know that doing a full SVD to get an orthogonal matrix is computationally heavy. It's basically O of m squared n, or mn squared. You obviously cannot do that on every single step of training.
No, it would completely kill your throughput. The authors here, much like the original muon paper, use Newton-Schultz iterations.
Right.
This is an iterative method to approximate the matrix square root and inverse. It allows you to project onto the orthogonal group incredibly efficiently on a GPU.
But Newton-Schultz is an approximation. It adds its own layer of noise.
It does. And that is actually another fantastic argument for NAMO. Since Newton-Schultz isn't perfectly orthogonal anyway, having an optimizer that is intrinsically robust to noise like NAMO-D might actually help mitigate the errors introduced by the approximation itself.
Oh, that makes total sense. It's like layering robustness on top of approximation.
Exactly.
Another detail I wanted to ask about, weight decay. How exactly does NAMO handle that?
So this is a subtle but really key point in the implementation. In standard AdamW, weight decay is decoupled.
Right. It's just a straight subtraction. Theta minus learning rate times lambda times eta.
Yep. But in NAMO and NAMO-D, they apply the adaptive scaling to the decoupled weight decay as well.
Oh, interesting. So if the signal-to-noise ratio says, hey, slow down, it scales down the weight decay too.
Exactly. If alpha sub t, or that diagonal matrix D sub t, shrinks the update, it shrinks the regularization proportionally.
So it ensures that you aren't over-regularizing noisy parameters.
Right. It's a very principled integration.
It really feels like they stripped the update rule down to its absolute first principles. Like they asked, what is geometry and what is noise? And merged them mathematically rather than just heuristically throwing things together.
Yeah, it definitely feels significantly more rigorous than some of the Frank-Antomizers we see popping up on RSkiv every week.
For sure. So, bottom line. If you're an ML engineer listening to this right now, and you're currently training a llama variant or a large vision transformer, should you switch to this?
I would say if you are already experimenting with Muon, absolutely. NAMO provides the exact same efficiency benefits, but with a massive safety net.
And if you're stuck on AdamW and scared to switch because of stability issues,
then NAMO is probably the exact bridge you've been waiting for.
and the code is totally open source, right?
Yes. The authors released a really clean PyTorch implementation. It's basically a drop-in replacement.
Awesome. One thing I'm still thinking about is that clamping parameter, C.
Yeah, the 0.1 to 0.9 shift.
Right. We saw it move drastically as the model size tripled. If we extrapolate that to a 7 billion or a 70 billion model, does C just hit 1?
It might. Or, and this is pure speculation here, maybe we actually need a dynamic C.
Dynamic in what sense?
Well, over the course of the training run itself, maybe early in training when the gradients are totally wild and the loss landscape is incredibly rough, you want C to be approximately 1.
To enforce strict geometry and prevent early divergence.
Exactly. But then, as you settle into a valley later in training, maybe you relax T4 to allow for fine-grained neuron adaptation to find that exact local minimum.
Oh, I like that. It's like a learning rate annealing schedule, but specifically for the optimizer's geometry constraints.
Exactly. Or, maybe it's the exact inverse. Maybe you start loose and tighten up. The paper doesn't explore dynamic clamping, but given how remarkably sensitive the 355 million model was to that parameter, I bet there are massive gains to be found there.
That sounds like an amazing weekend project for anyone listening who has some spare GPU compute lying around.
Definitely.
Well, the paper is Adam Improves Muon. And it really does seem to completely live up to its title. It's not necessarily replacing Muon, it's maturing it.
Yeah, it's moving us toward true structure-aware optimization that doesn't just ignore the realities of stochastic noise in the real world. It's a very healthy direction for the field.
And for those of you who want to dig deeper, Algorithm 1 and Algorithm 2 in the actual paper are very readable. You can see exactly how the Frobenius norm feeds into the bias correction.
It is absolutely worth looking at the pseudocode just to see how simple the integration actually is. I mean, it's only a few lines of code difference from standard Muon, but the theoretical implications are just massive.
Yeah, it's brilliant. That wraps up our look at NAMO and NAMO-D. It's rare we get an optimizer paper that feels this actionable right out of the gate.
Agreed. Usually it's a lot of dense theory with extremely marginal real-world gains, but the stability boost here is the real product.
Totally. Go check out the repo, maybe run some ablations on that clamping parameter yourself, and let us know what you find. I'll see you next time.